I started, welcome to Trager's Defense. Trager has been here for many years. Trager was an undergrad here, and now almost done with his PhD. Going to Lawrence Livermore, assuming he passes this.
Awesome. Thank you all for coming. It's great to see you all here, and then everyone on Zoom as well. Just see if I have all the technology working. Awesome. So today, I'm just going to be defending my dissertation here, which focuses on looking at the transition to inverter-based resources. And primarily, the focus here is looking at stability of AC power systems as we integrate more inverter-based resources into them. We're going to cover 3 different topics here. But first, for the outline of this presentation, we're going to start off just motivating why do we care about inverter-based resources, what's happening in the current kind of state of affairs with the grid. Then we're going to look at talking about considering current limits for inverters and how those impact stability of the system and their ability to ride through faults. Then we're going to look at stability of systems that contain many inverter-based resources, and then looking at what happens there when we want to consider system strength and how we can quantify system strength. Then we're going to look at voltage regulation, considering inverter-based large loads. One example of that here is data centers, which we've been hearing about in the news a lot recently. So why do we care about inverters? Well, renewable energy generation has been growing in the grid historically, and is projected to continue growing here. This is electricity generation globally by resource, and projected by 2050 here to have 50% of our generation being coming from inverter-based resources here, primarily wind and PV. Looking at battery energy storage, which is also interfaced to the grid, the amount of installed capacity of battery energy storage has been growing exponentially in the past few years. Here, plotting it out for 2024, that exponential growth has continued. Last year's in 2025, I think it was not quite as exponential, but still 112 gigawatts of additional capacity added to the grid. So clearly there's demand for having inverter-based resources in the grid. However, there's still a question of how to best control these inverter devices. Luckily, they have digital controllers, and they're very flexible and fast in how we control them, but they still have some physical limitations of the device itself. And then also, we're still trying to figure out exactly what the best way to control these devices is, especially in large systems when we have many inverter-based resources. Some examples of some events somewhat recently. Here back in 2024, down in California, after some typical fault was cleared, during the fault, 532 megawatts of inverter-based resources decided to disconnect from the grid instead of remaining connected to the grid, prioritizing protecting themselves instead of continuing to provide power to the system. Luckily, there weren't any kind of cascading faults following this, and the grid was able to recover, and those inverters were able to connect back to the system, but just showing that there is kind of a clear need for stronger controls for these systems, or at least an ability for them to handle kind of typical faults that happen in our system often, especially as we get higher and higher penetrations of inverter-based resources in the system. Looking down in Australia here at a different case, they were seeing repeated 15 to 20 hertz subsynchronous oscillations starting in 2020. In this zone here is called the West Moray zone. This zone is typically known for having kind of low system strength. There's not many synchronous generators, which are kind of the traditional devices that provide strength in the system near this area. And then there's been a large growth of IBR penetration, specifically PV inverter-based resource plants in that area. They kept seeing these oscillations occur, and for a while, I think until around 2025, they weren't able to actually identify what was causing this. And they weren't able to use or identify this using kind of just traditional grid strength metrics, and they had to look at using some more advanced models for the system. More recently, we've been hearing about data centers in the grid and the impacts they've had. Just earlier this month, NERC actually issued a level 3 alert, which is just kind of a notification to all the different entities in the system that it's relevant to, saying that they need to write up some reports regarding the challenges that these data centers have been imposing on the grid. The kind of primary 2 challenges that they outlined here was looking at large ramping of these loads. So the fact that these data centers can go from consuming relatively little power to large kind of steps here in very short amount of time. Here, just over the time of seconds, going from around 0.1 to 0.6 per unit, which for like a 1 megawatt or larger data center is a lot of power draw increased in a short amount of time. And also the fact that these data centers, they are prone to just tripping or disconnecting from the grid and going to their own backup resource anytime there's some issue with the quality of voltage in the grid, or potential, if they think the grid, something bad is happening there, to prioritize their own reliability, they might just disconnect. There's an event here where 1,500 megawatts of data center load just disconnected from the grid all at once. Luckily, the system operators were able to handle that fault and kind of hold it back and keep the system stable. But it just shows kind of having these devices that can quickly disconnect from the grid provides even more of an issue or challenge for the reliability of the bulk power system. So today I'm going to talk about kind of 3 challenges related to those events. First, we're going to talk about device current limits, then system stability, and then lastly, looking at voltage regulation for these large data center loads. First, before getting into that, just talking a bit about the inverter devices themselves. So these devices are used to convert DC or direct current power to alternating current power that's actually compatible with the bulk or large-scale power system that we have today. The devices themselves are just composed of some set of around 6 switches or so, which are modulated to be able to provide what is close or roughly an AC signal on the other side. And then an LCO filter filters out all the switching ripple. With these devices, typically when we go to model them then, we just assume we have a balanced 3-phase system and an average switch model. So we can just consider it as some average voltage source here, and then some filter between our grid voltage and our inverter itself. For our control, we usually do that in the direct quadrature reference frame, which is a rotating reference frame that if we have it correctly aligned with our grid frequency, then these 3-phase alternating signals that we have in our system can get converted to these 2 signals, ID and IQ here, which in steady state are just going to be constant values, which makes it nice for control when you're trying to track some reference there. The typical kind of control layout that we'd have for an inverter device here will be some nested or loop controller here, where we have some output power control loop where we're trying to achieve some maybe active power set point and reactive power set point. Maybe we're giving a voltage magnitude instead. But what this outer control loop does is it then provides voltage reference points to an inner voltage control loop, which then provides current reference points to an inner current control loop, which then actually is what we use to modulate the voltage at our inverter terminals. So now talking about the first kind of challenge here through the lens of looking at the constraints that we have on these inverter devices, we're going to talk about device current limits. For these inverter devices, the amount of current that we can actually output from the device depends on what the switches that the device are made of or composed of is rated for. So looking at our 3-phase signals, we can only let the magnitude of each current kind of going through these switches to go up to some certain upper or lower limit. When we then transform this to a limit in the DQ reference frame, this becomes a circular magnitude limit on our ID and IQ values. They're just equivalent here if we make the assumptions we use for modeling of our system. This will be important later on, as a lot of the kind of control we're doing here is trying to control our inverter such that our states are constrained to this circular magnitude limit. So with our control system here, what we typically would do to be able to actually maintain that current limit is that we have some reference saturation block here. So whatever the provided ID and IQ reference values are, we just saturate them to be within that current magnitude limit. And then assuming if this inner current control loop acts fast enough, then our currents won't go beyond that value. However, we kind of have a challenge that comes up then with this nested control loop structure, where we need to coordinate our outer power control loop with these inner current control loops, given the fact that our power control loop might be requesting references that we actually might not be able to achieve, which can destabilize our system. So the question we had here is, how do we design controllers that guarantee stability and safety considering current magnitude limits? And we did a few sets of work on this. The first one was looking at stability with a current limiter, just kind of as shown in that control diagram that we had. From our results, we showed that if we have a certain condition on our controller, we will converge to our actual reference point. And if we don't have that condition, then we might get stuck somewhere along our current magnitude limits. The next set of work that we did was looking at, instead of having that inner current magnitude limiter, if we instead try to augment our power control loop, here we did that with a safety filter to make it so that our power control loop would actually never lead the currents to be outside of our current magnitude limit. Here we can see this green line is intervening and changing our control that would otherwise be that blue line to keep us within the current magnitude limits and converge to our reference point. And then the last kind of bit of work here we did was taking something of a step back here and seeing, instead, if we want to just optimize some trajectory or solve some optimization problem with a dynamical system, how can we control that system to do that with some iterative updates to be able to then eventually try to apply this to inverter-based resource control. So that's kind of the question that we are going to talk about and focus on today with this section. So given a constrained optimization problem, how can we drive this control system to optimal points of this problem? So if we just have some nonlinear program here, our cost here is just C of x. We have inequality and equality constraints that we have to satisfy and make sure that x satisfies at our solution. We denote our feasible set to just be all points of our variable x here that lie within those constraints. And then if we just say that xref or x star here is just a locally optimal solution for this nonlinear program, then what we want to do is see, can we solve this nonlinear program for xref while guaranteeing that our variable x here is going to remain within the feasible set in each iteration or update that we apply to that state. In the literature, there's a nice approach here called safe gradient flow, where what they do to try to solve this problem is they actually define these dynamics for kind of the updates that we want to take to our variable x here, where we're just following along, doing gradient descent in the direction that would minimize our cost. And then we have these two additional terms here where we add these inputs mu and nu, and those mu and nu inputs are used to ensure that the states remain within the feasible set. How do we actually select mu and nu from that? We just pull from control barrier theory, and we get these two kind of linear constraints that as long as you're selecting mu and nu, such as these constraints hold, then our variable isn't going to go outside of the boundary that we have. To be able to kind of solve for these, that's minimally optimizing that gradient descent direction that we want to follow, we can solve this quadratic program here, which is just trying to minimize essentially the impact that mu and nu have on our trajectory. Applying this then, say if we have some cost function, we just want to minimize this x1 value as our cost, so our gradient's just pushing towards the left. But we have this circular magnitude limit. Our state, using this approach to try to optimize this variable x, it will go towards the left, and then as we approach that barrier, we're going to start to have our mu and nu values that we're solving for in each iteration, push it away from that barrier until we actually get to our optimal point considering this constraint. However, we can't just directly design our dynamics when we're thinking about control systems. So assuming if we have some control system where we have these nonlinear dynamics here, x dot equals some function of our state in our input, and we have some similar constraints here in terms of our state and our input, an equality and an inequality constraint, then we're going to have to select u such that we're controlling x considering the dynamics that we have of our system. So the question we ask then is, how do we design a controller that can drive the state of our system to solve this nonlinear program that we want while guaranteeing that our state is going to remain within this feasible set at all times? And the solution that we propose for that here is that we discretize our dynamics and then form this trajectory optimization problem, which we can then directly apply this safe gradient flow approach to. So here, we're just putting the dynamics here that are discretized as an additional equality constraint into our essentially rolled out trajectory optimization problem, which at least for that final state can be thought of as equivalent to our nonlinear program, as long as we align it with that nonlinear program here. Okay, so what does this look like when we actually go to apply it? Here we just call this safe trajectory gradient flow. And then essentially for each time step, what we're doing is for k iterations, we're applying some optimizing updates, applying that safe gradient flow to the trajectory optimization problem we have. Looking at this plot over on the right here, we can see how if we take some optimizing iteration, our trajectory might change like this. We take another optimizing iteration during that time step, and then we step forward in time. We continue taking more optimizing iterations like this, take another step forward in time. At this point, if we take optimizing iterations, we're actually not going to change anymore, and then we're just going to actually converge to our xref value there. Looking at this applied to just a linear system here, defined just in the upper right, where we first need to increase x2 before we can actually shift x1 over, we can see how that our trajectory here is going to iteratively becoming more optimal within each time step. We're not going to get quite to what the optimal trajectory is. Looking down at our inputs here, we're going to be delayed a bit. It's going to take some time to solve towards having an optimal trajectory, but we are eventually going to reach our kind of reference point that we want to get to here, considering the dynamics of our system and going, at least moving towards an optimal trajectory over time. To then apply this to grid forming inverters, what we do is we define this cost function here, where we're incentivizing having our active power and reactive power go towards some reference values, and then we're decentivizing varying from our nominal voltage magnitude and our frequency that we have for our system, just that nominal frequency. Applying this then to the nonlinear dynamics that we have just for this representation or model of our inverter, considering the current magnitude limit that we have, we go ahead and apply the safe trajectory gradient flow approach. We just look at it here in simulations, comparing just for a step in these power references to see how the controller reacts. And we're going to compare it to model predictive control, which is similar, but it's actually completely solving the optimal kind of trajectory problem in each time step, while our safe trajectory gradient flow is only providing some limited optimizing iterations to kind of updating our trajectory. Then we're also going to be comparing to droop control here, which has an additional synchronizing term to make sure it actually remains stable and comes to some steady state point. So looking at the simulation results here, in this bottom left plot, we can see that all of the controllers eventually get up to the current magnitude limit that we have. Here we're just plotting the magnitude of our current, but we can see that their states converge to different points, or at least for the droop control, it converges to a different point. But for the model predictive control, which is kind of our baseline, and our safe trajectory gradient flow, they converge to the same point. Looking at our outputs, which and our inputs here, which are more related to kind of the solution of our nonlinear program that we've defined by that cost function, we can see that both the MPC and the safe trajectory gradient flow converge to some optimal point. But our safe trajectory gradient flow takes a bit more time. So you might ask, why not just use MPC? And for this, the limitations that we have is that if we're trying to actually apply this on some inverter device, that inverter has limited kind of computational power. There's just some small digital microcontroller used for that device. And we need to be able to solve this problem fast enough so that we can actually apply these controls that we derive within each time step. Here in this simulation, our time step is 1 millisecond, and we can see the model predictive controller is usually taking somewhere around 20 or 30 milliseconds before it hits our constraint. Once that happens, we actually have one iteration that takes all the way up to 300 milliseconds to solve that model predictive control problem, which would make it kind of infeasible to apply for an inverter device, at least at scale with many inverters with kind of smaller microcontrollers. For our safe trajectory gradient flow approach, it's usually taking below 1 millisecond. In one iteration here, it takes above that, which kind of shows that there's room for improvement here, especially kind of in how we're solving these quadratic programs to make it less computationally burdensome to make this method applicable. But it is kind of orders of magnitude faster than fully solving that trajectory optimization problem with model predictive control. Okay. The next set of topics, or kind of the next bit I'm going to talk about here, is looking at system stability. And in particular, this work was actually done with some folks in collaboration that work at the National Lab of the Rockies. I was there for the last summer as an intern, where I started this work. And here, the focus that we had was looking at system strength, where system strength refers to the ability of an AC power system to be able to maintain a stable voltage and frequency under all operating conditions. This is a pretty general definition, essentially just saying we want to keep our system stable. But a lot of the times, kind of what this definition, or at least the way that it's applied in industry, is used is looking at the system in steady state and subject to small disturbances. So kind of just looking at the small signal stability of our system. And the general idea for system strength is that if our system is strong, then the sensitivity of our voltage or frequency to disturbances is low. And in weak systems, we have higher sensitivity, so we're more susceptible to our system becoming unstable. A lot of times, we want to be able to quantify our system strength through different metrics. We're going to talk here a bit about the traditional metric that has been used here, short circuit ratio, which has been useful for trying to figure out in systems with low inverter penetrations, when you add an inverter to a point in the grid, is it going to be stable or not? Here, SCR, or short circuit ratio, is just defined as the ratio between the short circuit current at that point of interconnection. So something of an idea of how much support it's getting from the other synchronous generators in the system that might be far away. We might have lots of impedance, so we might have a lower short circuit ratio. Or if it's nearby, we usually would have a higher short circuit ratio. And then we compare this to the rating that we have of our inverter device to get an idea of relative to our device's side and how it's acting, how much support it'll get from devices in the rest of the system. If we have an SCR below 3, we can usually say the system's weak. Above 3, we say the system's strong. And in weak systems, grid following inverters, which are the conventional way that we control inverter devices, can become unstable when connected to weak grids. However, SCR, just a low SCR, doesn't necessarily imply that an inverter-based resource will be unstable, and even having a high SCR doesn't necessarily mean that our device will be stable. And to actually be able to understand stability, we have to do more of a system-level analysis, considering how devices might interact, and then also derive something called the critical short circuit ratio here, which is essentially just the SCR value for our system, that if it's below that value, will be unstable. If it's above that value, our device will be stable. So you can see here, SCR isn't able to fully consider kind of stability very well without having to actually simulate the system, finding what this critical SCR value is. And it doesn't quite capture all the potential interactions that can be happening. So instead, if we look at small signal stability approaches, so if we're looking at the eigenvalues of our system, we might be able to get a more accurate representation of how our system behaves or how sensitive our system is to at least small perturbations. What we can say here is if all of our eigenvalues are in the left-hand plane, then our system has adequate damping for all of its modes. They're going to converge to some new value, or at least the same value here. It's a little off. If that eigenvalue somehow gets pushed to the right-hand side for some change in our operating mode, our system will be unstable. We'll have inadequate damping of at least one of the modes. If we're pushed towards the right-hand side here, we might have poor damping. So if our imaginary part of this eigenvalue is much larger than the real part, we might have sustained or just poor damping, or this oscillation might take a long time to be able to get dampened out. But just looking at the eigenvalues might not be enough to understand the system strength that we have for a system. Here, let's say for one system, and system 1 and system 2, we have one eigenvalue that starts in the same place. But for system 1, after some perturbation, say our eigenvalue is very sensitive, it gets pushed to the right-hand plane, our system becomes unstable. In the other case here in system 2, this eigenvalue might be less sensitive due to the way that we're picking our parameters, and our system might be stable after that. So we get some insight that looking at the sensitivity of the eigenvalues is actually an important way to kind of try to quantify our system strength, in addition to just seeing whether or not our system is stable or unstable in one state. One way to try to look at the eigenvalues or the small signal stability for our systems is essentially just linearizing all the nonlinear devices we have in our system and defining something called the equivalent admittance model here. So here we have some nonlinear dynamics for our inverter device. If we linearize this and then take the Laplace transform, we get this transfer function matrix that represents this equivalent impedance of our device, which is essentially characterizing how, at least for small perturbations around some operating point, how our output current will vary in response to some input current. But it's important to note here, that we'll see later on, this depends on our device's operating point as well and changes because our device is nonlinear. When we have all of these different equivalent admittance models for the different devices in our system, and we actually want to go ahead and look at the stability of our entire system, what we can do is use this whole system admittance model, which is proposed out of a group at Imperial College, where we stack up all of our device equivalent impedances into this whole transfer function matrix here. We just call it ZDev. And then we define this equivalent admittance model for our network here, which essentially just represents the dynamics of our lines. And then if we connect all these together, we can get this whole system admittance model from the individual device equivalent impedance models and our network admittance models. This forms something of just a feedback loop here between our device and our network. And from this, we have our whole system admittance model as follows here, from this feedback loop. Using this whole system admittance model, what we can do, or this whole system admittance model, it characterizes essentially for some perturbation, say in voltage at one bus, how the current at another bus responds. And using this whole system admittance model, we can actually have that all of the poles for all the different elements within this whole system admittance model are the denominator of all of these elements of this whole system admittance model are equivalent, and just solving from one of them for the poles of that transfer function, we can find the poles of our system, which are equivalent to the eigenvalues of our system to evaluate whether our system is stable. Further, from this whole system admittance matrix, looking at the residue of this whole system admittance matrix, which is just defined as follows here, we can know, based on some other existing work out of that group, that those eigenvalues or the sensitivity of those eigenvalues to changes in our equivalent device impedances are related to that residue value. So here, this gives us some insight into if we perturb this device impedance matrix, how will our eigenvalues shift, at least kind of giving a first order approximate of that. And then what we'd actually want to know, though, usually is how does an eigenvalue change with respect to some system parameter x, whether that be a control parameter of one of our devices, or potentially even an operating point kind of parameter, so say a power injection, and we want to see what happens to our eigenvalues if this parameter that we're perturbing is going to perturb lots of other parameters in our system, which will impact lots of other equivalent admittance matrices, which will move our eigenvalues in our system. So the question they asked here is kind of how can we calculate these eigenvalue sensitivities to a change in an operating point, and then how can we use those sensitivities to quantify system strength? So say we just have this 4-bus system. If we decrease how much power we're injecting at bus 2 in this system, we're going to see a change in how much power is injected at all the other buses. If we're going to end up coming to some new steady state value, we'd likely have some increase in power from here, what's represented as our slack bus, and then we have changes in our voltage and angles at the other buses, further perturbing kind of the equivalent admittances of these other devices. What we can do then is if we calculate what those perturbations in our power flow would be in response to a change in the power injected at some other bus, we can go through and see how does that change in our power injection result into some perturbation or change in our eigenvalues, using just kind of applying chain rule here along here using the power flow sensitivities. And then if we can measure our device level impedance sensitivities to local power perturbations, and then if we have our eigenvalue sensitivities to changes in our equivalent device admittance, applying through this chain, we can get an idea of for that power injection change, how much our eigenvalue is going to be perturbed. From this, using these sensitivities, we define these sensitivity indices at an eigenvalue level here. So for some change in this parameter mu, which would represent either an active power injection change or a reactive power injection change, and then for this eigenvalue r, we look at how large is the real part of the perturbation in our eigenvalue, so how much is it being pushed towards the right-hand plane, and then we divide by that real part, or the size, essentially, of how far away from that imaginary axis is our eigenvalue, to get an idea of how sensitive that eigenvalue is to that perturbation in that parameter mu. Further, then, we define these metrics at a bus level, which are saying, looking over all of these eigenvalue sensitivities, what's the maximum kind of push towards the right-hand plane, normalized by how large the eigenvalue is, for an increase or a decrease in that value. With these sensitivities, if we go ahead and plot the heat maps of these sensitivities, what we can see is which buses and for what parameters the system is most sensitive to and most likely to potentially become unstable after a perturbation. So here we can see at bus 8, for an increase of active power at that bus, the system is sensitive to that and might become unstable. Next, we kind of ask what happens, or can we do this as well for looking at line admittances? So consider here that we have an outage of the line from bus 1 to bus 3. What happens to our system? How does this impact our eigenvalues? So if we represent this and look at kind of just a small perturbation on the admittance of that line, instead of looking at fully taking that line out, we could then see and calculate how that impacts the different powers and voltages at all the different buses. And then using a similar kind of approach as before, we can figure out how that perturbs our device equivalent impedances and then perturbs our eigenvalues through that path. Here, though, since we're modifying the admittance of one of our lines, we also have another path here where we're perturbing that network equivalent admittance matrix that we have, which also has a perturbation effect or a sensitivity that our eigenvalues have to that. Going through both of these paths, and then since we're just looking at kind of these first order sensitivities, when we add those two sensitivities together, we can get the true perturbation, or at least first order approximate perturbation of that eigenvalue, and then similarly define kind of metrics based on those sensitivities as we did with power injections. So to kind of test this approach, we look at a 118 bus case study. This is work that we just recently submitted to the Transactions on Power Systems. And in this, with this modified system, we have significant IBR penetration. We have 3 synchronous machines throughout the system, 4 grid forming inverters, and then 19 grid following inverters. going ahead and calculating the line admittance sensitivities for an increase in line admittance. So if you somehow could switch another line on in that case, or a decrease in line admittance, giving an idea of if we have an outage of that line, how sensitive our system is to that. We see that the line from bus 103 to bus 110, the system is highly sensitive to, and then bus 100 to 103, our system has a low sensitivity to. So to validate this, we went ahead and ran some time domain simulations here, where at 0.5 seconds, we turn off that line that the system is not very sensitive to. We see the system is able to converge to a new steady state operating point, and the system remains stable. At 1 second, we turn that line back on. Then 1 second later, at 2 seconds, we turn the line that the system is sensitive to, the line from bus 103 to 110, and we see that our system actually becomes unstable. We get this undamped growing oscillation that appears due to an interaction between the lines and some of the grid following inverters in the system. And our system would eventually have a blackout here if we don't have some intervening actions. Looking at a nearby grid forming inverter, we can see it's also unstable after this, so it's not just kind of our grid following inverter disconnecting from the grid weirdly there. Looking at kind of how our prediction of how that eigenvalue would change with this first order perturbation and comparing it to the actual nonlinear trace that that eigenvalue is following, we can see it's not perfect, but it does give us a good approximation and understanding of how sensitive the system is to that perturbation. Now looking at seeing if we can find some remedial actions to restabilize our system after that line is switched off, or potentially we might want to take these actions ahead of time. But here just looking for our unstable eigenvalue, looking at the sensitivity to increases in reactive power at certain buses in our system, and then increases in voltage at certain buses in our system. We can see our system is very sensitive to increases in reactive power at bus 112, and it's also very sensitive to increases in voltage at bus 100. So if we do the opposite of these actions, if we decrease the reactive power and we decrease the voltage, we do that here just a little bit after the line is switched off, we can see that our system actually becomes restabilized. We get adequate damping and we converge to a new steady state point. Switching the line back on a little bit later, our system then remains stable after that switch. One thing to just note here is calculating these eigenvalue sensitivities by just perturbing and resampling the eigenvalues can take a long time, especially for large systems. When you have thousands of states and you want to solve for the eigenvalues, it can take a good amount of time to solve for that. But our method here that just uses calculating the sensitivities takes only a fraction of the time. In the 118 bus case system, it takes only 2% of the time that we have, or we would otherwise be calculating here using this kind of perturb and resample method, noting here that this is a log axis that we have. Okay. The last bit of work that I'm going to talk about here is looking at data center voltage regulation and trying to handle essentially these kind of large steps that we have in our power and how these can impact the voltages throughout a distribution system. So why does this happen? Essentially, when we're trying to train large language models or other AI models, there is a compute phase and a communication phase. During the compute phase, the load is kind of distributed across many computers or GPUs, and they're all running at somewhat of max power, working on training or finding different updates in the model for different kind of samples or test data. Then, after they complete that certain epoch, they come together, they communicate, and they update the whole model that they're using based on the different gradients that they solved for. This repeats, so we get this area of high load dropping down to low load, high load again. At each point, we have some variation and potentially even some large dips. But in general, we can think of this as just stepping between 2 points. If we look at how this impacts the voltages of throughout our distribution system, even just the voltage here at the bus that data center is connected to, since our lines have significant resistance in the distribution system, it shows that when we have these large steps in active power, we're going to see similar steps in the voltage of our system, proportionate to the resistance of the lines in our system. Here, dipping us well below our kind of plus or minus 5% that we'd want to achieve. Looking at how reactive power could help in this case, maybe we just want to shift this up. If we increase or inject reactive power at that data center bus, we're going to be more centered around our nominal voltage, but we're still going to have these large spikes here, which we'll talk about a little bit later on. So the first question we kind of ask is, how can we use inverters reactive power control to regulate voltage deviations from these large fluctuating loads? And looking at our data center load model here, just as we had before, we can define here during the compute phase, say we're in mode 1. In the communication phase, we're in mode 0. And we can define this kind of model that represents how this load is dependent on what mode we're in, and then we have some additional intermode fluctuations. If we just, for now, ignore those intermode fluctuations, then we'd say we have this kind of idealized step load that we have going between a high and a load point, depending on what mode we're operating in. And then if we go ahead and apply what would be some typical kind of conventional control here with just a decentralized volt-var droop controller, where we're trying to push our voltage to just be at 1 using this kind of droop control updates here, we'd see that after each step in our power, then our voltage is going to see some kind of proportionate step. We're going to then control our reactive power to go back to 1 before we see another proportionate step going down. So overall, we get a pretty large variation between our maximum and minimum voltage values that we have. If we instead kind of consider what these steps are going to be, and we'd use some switching reference control, or at least for what this VREF value is, to achieve something of a static reactive power injection, we might instead be able to control our voltage so that we're centered around what this nominal voltage value would be, which overall will minimize kind of our deviations from that nominal voltage value. So the kind of control that we proposed in this paper here is, instead of just trying to regulate our voltage towards 1, we have a switched reference that's based on how our load profile is impacting the voltage in our system. Here, this switching ref controller is decided in each time second based on some bias term that we have to calculate and update, and then a voltage amplitude term that we have to figure out as being proportional to how large these steps are. We also have this switch term, which is switched between +1 or -1, depending on what mode we're in. And in the paper, what's shown is that if we correctly select that amplitude to align with our voltage steps, then our switching reference will essentially ride along how our voltages step, and we can have it so that it aligns with whatever our voltage ref is. And then if we update our bias term of our voltage reference term, then we can shift this term to be centered around 1. To actually apply this in the system, we don't just inherently know what this bias term should be, how large our steps in voltage are between the modes, or what mode we're in even, so when those steps occur. So what we do is we use these measurement-based reference adaptations. So for the voltage magnitude, we're just measuring over the past historic steps that we have to see what's the largest step between each time. For the voltage bias, I think I might have updated it if you're wrong, but we're essentially is looking at the difference between the maximum value and the minimum value, looking at where its average is, so the middle of that voltage waveform, and then updating our bias here slowly to converge so that our voltage is centered around 1. And then lastly, for the switch mode, we see that when our voltage goes above the bias term, we say we're in the high power mode. When it goes below that, then we say we're in the low power mode. We test this on a 33-bus distribution system here, where we have a data center up at bus 22, and we're running this large language model training load as shown below. With these results, comparing to a fixed reference controller, which is just trying to drive the voltage to 1, we can see that we have these larger deviations in each step as it's trying to regulate the voltage to 1 before that step occurs. With the switching reference controller, after a bit of time, we converge such that the steps within our voltage are centered around 1, and we have at least better performance within the plus or minus 5% limit that we have. However, you might still notice we have still large steps in our voltage, so this kind of motivates having some more control, at least on the active power side, and some internal regulation of the data center. So the question we ask then is, how can data centers regulate their own load to limit their impact on system voltage deviations? Even if we're running some kind of reactive power compensation like this, we want to minimize those voltage deviations, so we're going to want to minimize the steps in our load. Looking inside of data centers, the way that they're connected to the grid, they usually have what's called an uninterruptible power supply. This device essentially just operates so that if the grid goes offline, it has some amount of energy storage that's able to bridge the gap between when they can turn on the backup generators they have in their system, which would be something like diesel generators to be able to supply the load. But the storage that they have in these uninterruptible power supplies will be rated to supply the full load of the data center for 1 minute, 5 minutes, depending on kind of the redundancy levels of the data center. We also have further downstream these power distribution units that essentially is take power from the UPSs and send it to all the different computer racks that we have throughout our data center, or the different clusters that we have for computing. Data centers need to maintain a certain level of redundancy, at least to get certain kind of high value customers. So what they usually have is lots of redundant components and alternate paths, even potentially different connections at different points in the utility system. But in addition to this, they also have usually additional UPSs and pretty much a good amount of energy storage available to be able to make sure that if something happens, even in the case where one of these uninterruptible power supplies goes offline, then we're going to have enough energy to satisfy our load until a backup generator comes online. So the question that we ask here is, can we utilize the energy storage in these uninterruptible power supplies for voltage regulation of data center loads while maintaining the redundancy requirements to be able to satisfy that load for whatever that backup time that we have is? To go about looking at this question, the first thing we did was we formulated these constraints, essentially saying how much energy do we need to provide from each uninterruptible power supply to the storage racks or the server racks based on how the uninterruptible power supplies are connected to the server racks. However, a configuration like this isn't very common in data centers. Usually they'd have some configuration like this where they just have an extra UPS, somewhat deemed the swing UPS. And in this case, we can kind of simplify a lot of those constraints down. So in the case where that swing UPS is out, each UPS just has to be able to satisfy its own load here. So here, E is how much energy we have in the UPS I, and then D sub J here is how much load we have at server rack J. Here, this I should just be, or J should just be an I. So it's saying that the amount of energy that we have in our UPS has to be able to satisfy the server rack it's connected to. In the case where one of the other UPSs or the main standard UPSs goes out, then the swing UPS has to be able to satisfy the maximum load that we have over those server racks, as it might need to satisfy whichever one that its equivalent or corresponding UPS goes out. So this simplifies the constraints that we have. And then forming this into a trajectory optimization problem, here we're just adding those constraints down here. And then defining a cost function here, where we are defining the first part of this cost to be the performance of our grid side load trajectory or power trace demanded by the data center, where this first term is trying to minimize the maximum deviation from the average value of our power trace, and the second term is minimizing the intra-time step in our power demand. We have another kind of set of terms here, which are the degradation costs, which is in terms of trying to understand how much impact dispatching that storage has on the actual degradation of the storage, or how fast or how long it's going to be until we have to replace that storage unit. Here, that's just a squared term on how much power we're actually dispatching from the storage, and then a term that looks at how far we deviate from what we say is our nominal SOC or state of charge for the system that we want to achieve. However, to actually be able to use some kind of predictive model like this or trajectory model, we need to be able to predict what our future loads are going to be. So we're going to have to use some predictor. Here, basing it off this past load, if we feed that to this predictor that our collaborators have trained and what we're working with, we're able to get this output here, where inherently we're going to have some errors between our predicted load model and the actual load. Here, the two ones that we mainly want to look at is how the change or errors in when that step is being predicted as occurring. So here, we're predicting the step to occur a little bit early, and then later on, we're predicting it a little early again. And then how that impacts the amount of backup energy that we think we need for the future loads that we're predicting. So looking at these challenges here, if we have a kind of delay in our prediction against whatever this true load step is going to be, say we want to regulate or dispatch our storage to be able to regulate this power trace to be at some nominal value. If we try to regulate it based on our predicted value, we're going to start injecting power a little bit too late. So when we're regulating and trying to bring this load at the low state to be higher, once we actually get the true step, we're going to get a large step here according to the actual step in that power trace. And then overall, we're going to get larger power deviations than what we had before. Looking at kind of the impact that some delay in our prediction has on what we think our backup energy requirement is, if here we have this delay in our prediction, we'd think, oh, we can dispatch our storage as follows here, where we're following along how much backup energy we think we need in each time step. However, at certain time steps here, we're actually dipping below what the true energy demand throughout that future backup horizon will be, and we'd have deficits in the event that we'd have an n-1 case, and we'd have to disconnect from the energy grid. So to handle kind of the first of these challenges here, just the mistiming of that step, we designed this hierarchical control architecture here. We have an outer control loop, which is running model predictive control on that trajectory optimization problem. It's essentially just providing then a desired kind of optimal trajectory to this inner control loop, where the inner control loop is just essentially acting as a filter, where we look at the difference between this desired trajectory and whatever the actual power draw from our data center is to be able to dispatch our storage to try to regulate ourselves to this inner or desired optimal trajectory. The reason we can't just update our outer loop fast enough to be able to handle any of these steps is that it takes time to be able to solve that model predictive control problem, and it also takes time for the predictor to actually make a prediction. So we can only update the outer loop at, say, 1 to 10 seconds, but we want to be updating this inner loop much faster. Maybe we'd say in the range of 1 to 100 milliseconds. Next, we look at potential issues with having mispredictions on where that lower energy limit that we'd have would be. So here, if we say this is our actual power trace, we trace out what that backup energy requirement would be here. Then if we say we make some prediction, we do a similar thing for tracing out how much backup energy is required from our prediction. But we notice here our prediction has errors. Sometimes in our backup energy requirement, our predicted model is saying that we need less energy than we'd actually need. If we look over many different kind of traces and testing over lots of different kind of potential loads that our data center could have, what we can do is find this 99% barrier around what the actual required backup energy would be. And we can say that 99% of the time, our predicted backup energy requirement will stay within that buffer. If we add that buffer to what our predicted energy or lower limit requirement would be, we can find a limit that at least 99% of the time, our required backup energy will fall below that limit. So applying those two things to our model predictive controller, or just our control approach, we compare this to what we just call kind of a proportional droop control, which is being fed just a historical average of our load and trying to regulate our load based on that historical average. And we compare that to our hierarchical model predictive control approach. Similarly, we have the same setup as before, a data center at bus 22 with this training load profile for an LLM. For the droop proportional kind of controller that we have here, to try to find a lower limit on how far we can dispatch that storage, we look over lots of different test data sets here. We've looked over 63 different kind of large language model training traces that we build up to be what the load would be for our data center. And then we can find the point that at least 99% of the required backup energy storage would fall below. We use this as the lower limit for our droop controller to get more of a fair comparison. This value also provides an upper limit on that lower limit that we're predicting, which makes it so it's nice to have a little bit less when our buffer goes beyond that point. Next, to actually find how that buffer from our predictor's error needs to be designed, we look at testing this predictor over all those data sets as well, finding what these errors are between the predicted and the actual load at each time step, and then looking at the cumulative density functions here to find the point at which 99% of our errors would fall below that point, and we use that as our buffer on those lower limit values that our prediction provides. Applying these then and then looking at the simulation results, we can see that our model predictive control approach can achieve a much kind of tighter regulation on our active power values, which ends up resulting in a tighter regulation on our voltage values. Zooming in a bit here, we can see how the model predictive controller, we have this purple buffer here around our predicted dotted purple line for that lower limit, and our control value skirts along the top of that buffer, being able to utilize a little bit more headroom than the droop control case can, and it's also more optimally dispatching our storage to be able to smooth our load profile to look something like this here, where we have lower ramps and less deviation from that minimum value, resulting in an overall lower cost for our hierarchical approach than this proportional group control. So talking about some potential kind of research directions branching off of this work. First starting off with looking at control of inverters with current limits. The first step would probably be trying to look at expanding or extending the safe trajectory gradient flow approach to be able to consider disturbances and exogenous inputs. So if our grid voltage has steps there, being able to measure the actual frequency of our grid voltage is another thing that we need to know to be able to apply this control approach. So seeing how we can best do that for the system, as well as seeing if there's some hierarchical control architectures that we can use, since at the moment, the safe trajectory gradient flow approach still takes a bit more time than we'd probably want it to if we want to be updating our control for our inverter system at around 10 kilohertz, which is generally common there. Further, investigating stability of current constrained inverters and networks and seeing if there's some applications for decentralized and optimal control approaches to be able to find guarantees on when these systems are stable instead of just looking at the device level as we've been doing here. Next, for the small signal stability sensitivity approach that we looked at, further uses for potential eigenvalue sensitivities are being able to kind of look at gradient descent approaches using these eigenvalue sensitivities to improve the robustness of the small signal stability of our system. Say we're at some operating point and we find that one of our eigenvalues or modes has low damping in our system, we might be able to use these eigenvalue sensitivities to see how can we optimally push different injections in our system or change different control parameters in our system to make our system more robust in terms of small signal stability. So trying to push these eigenvalues further towards the left-hand plane. Next, considering how the actual kind of transient behavior of the power system impacts where our new steady state is going to be after a transient in the system. So considering what the different power groups in the system are. In our approach, we just have a slack bus, which kind of picks up extra active power when we decrease active power at a different place in the system. But in reality, lots of different devices in the system are going to be picking up that power as the frequency drops before it comes to a new steady state. And this will impact where our device or that new operating point, which our devices are being linearized around. Lastly, for the data center voltage regulation, further looking at kind of trying to look at some analytical approaches to determine the optimal regulation capabilities for some limited amount of energy capacity we have, especially for a time varying amount of energy capacity, could prove some interesting results that might make it so we might not need to run a full kind of model predictive control approach with a prediction. And then lastly, investigating other large load profiles such as large language model inference, which will provide different traces that are less periodic and dependent on kind of what tokens people are using or what requests people are making to that model. But yeah. Okay. Cool. With that, I just wanted to acknowledge all the people that kind of supported me along the way here. My advisor, Professor Baozhen Zhang, everyone in my lab group who I've been happy to see. We've been having a bit more of kind of socialization going on, a bit of revival after COVID. Things have been growing there. All my collaborators throughout the years here on the different works, even going back to undergrad here when I was just starting off doing research. All my committee members being here, and then all of my different funders, as well as all my colleagues throughout the years, all the people at the Crag Climbing Center. And then lastly, friends and family. Sorry. Yeah, with that, thank you all.
Questions for Ron? Anybody from the audience? So if not, you guys will be excused. We'll do the first one.
Okay, I'm going to go ahead and end the Zoom call then. Thank you all for coming. Yep.